ago. And it's about social temporal networks and how to represent these. Indeed, we have nowadays a lot of an increasing number of data sets which described contacts or interactions of people with temporal resolution. So those are represented naturally as temporal networks, which are a succession of temporal edges. And sometimes we just aggregate all this temporal information to obtain a static weighted network. But if we want to apprehend the whole complexity of the temporality, it's usually not very easy to represent and to apprehend what it means. In particular, if we just look at the temporal network at a specific time, we will see only the edges that occur at that time, so the interactions of that time. So it's a very limited and partial information. On the other hand, what is usually done is to aggregate with a certain temporal time window around each instant, but then we have an important effect of the length of the time window, which is typically arbitrary. This is well known. I mean, that's a very nice paper from already 7 years ago about that. And also you have the same thing. If you aggregate from 0 to a certain time, you, as your time window increases, you are blurring the dynamics, you are losing information about what happened. So it's interesting to try to bridge this gap between the temporal network itself and kind of better representation. And there's a very nice preprint a couple of years ago by Mason Porter and collaborators that proposes to consider weighted ties between each pair of nodes in the network. And each time there's an interaction in the temporal network, you have a pulse in the weight of these ties, and then you have an exponential decay. However, these ties in this representation, they evolve independently, which whereas in a social network, you have ties that depend on each other. So our approach is to propose such a representation, taking into account the fact that individuals have limited resources, like has been long known from the Dunbar number, which has been documented also in phone calls by the work by Militello and collaborators, on Twitter by Bruno Gonçalves and collaborators. And so the idea is that each time there is an interaction between two individuals, it means that the tie between those two individuals is reinforced. And it also means that I and J are choosing to dedicate time to their tie, meaning they dedicate less time to the other people. And so it weakens the ties between IJ and the other members of the system. So basically, if we have a population of agents with temporal edges, the idea that we represent our temporal network, which is a list of interactions with their times between the nodes, as a weighted evolving network in which when I and J interact, the weight of IJ is increasing and the weight of the ties between I and other nodes and J and other nodes is decreasing. Of course, you can encode this into many different specific rules. We took a very simple idea with just one parameter. So the weight between I and J and I will increase by an amount that brings them closer to the maximum value. And the weight of IL and JL will decrease by the same factor. Here we have just, we can use W max equal 1 without loss of generality. So we have one parameter which quantifies how much the ties change when there is each interaction. And we also know that because the weight of I and L decreases, but not necessarily the weight of L to I, the network becomes a directed network. So once we have this framework, we want to apply that to some data. And we did that using a number of data on contacts between individuals in schools collected by sociopatterns and also by a group in the US. And also we'll see two interactions within a group of animals, of baboons. So first thing we looked at is that since these weighted ties now are directed, we looked at the reciprocity, and we took the opportunity of this data set in which we have both contacts and surveys concerning friendship, and we obtained that indeed mutual friends tend to have more reciprocal links, meaning that indeed they are reciprocating their attention in some sense to each other more than non-mutual friends. We also, so the next step is to look at what happens about network evolution and whether this representation can allow to detect changes in the evolution of the social system. And we use a similar framework as the one proposed by Naoki Masuda and Peter Holme, in which basically you look at the distance or the similarity between snapshots of the network at different times. Then you look at the matrix of distances between these snapshots, and you do a clustering that allows to attribute temporal intervals to states. There are a number of choices, of technical choices. We are using matrices of cosine similarity between the networks at different times, and we'll just illustrate what we obtain. So here we have data from a primary school in which we have the contacts between children during 2 days, and we see that as alpha is small, so there's not much change in the ties at each interaction, we don't see much structure, but as alpha increases, we start seeing structures in the data, which in particular correspond to the lunch times. And we even see substructures which correspond to the fact that the children go to lunch in 2 different batches. So indeed, it looks like we can extract interesting temporal structure in the social networks from this. We also use that in US school data, and we also see that we detect the assembly that occurred during the first morning of data collection. We also see the lunchtime, and we also see that we have a very different social system in the primary school and elementary school in the US, in which indeed children do not move at all in the classes in the same way. We also looked in data in which there is actually not a big change, so we impose a change by perturbing the data at a certain point, here by just switching to individuals in the data in a group of a few 13 baboons that for which we have data for a few months. And once again, we see that depending on the value of alpha, we can detect this artificial change in the data. Here in this case, we also see it using just daily aggregated network. But if we go to different time scales, such as a very quick change, once again, artificial change in the data during a couple of hours, then our framework can detect the change quite easily, while the aggregated network will not. So here we quantify that by looking at the JACA between the interval that is detected as perturbed and the JACA and the interval that is actually perturbed in the data. So I just wanted to show this few examples. Of course, we are now looking at different systems, other data sets, and we want to check what kind of, how the range of parameter values that allows to detect a perturbation changes depending on the systems, on the time scales involved. And obviously with also a bunch of synthetic temporal networks in which we can tune the kind of perturbations that we impose and check how we detect that. And there's also probably a different avenue that we want to have, which is to use an alpha. So we had just one parameter here, but it could be interesting to have 2 different parameters for the increase and the decrease of the ties. So thank you, and if you have questions, I'm ready to answer them.
Are there any questions? Okay, at chat there's a question. Does this representation help us with getting rid of arbitrariness of delta t?
So not yes and no, in the sense that we have now a parameter instead of delta t. We don't have any more a delta t. Our weights are evolving in time at each interaction, but we have this parameter alpha. So obviously there is still one parameter, but by changing this alpha, we can see that there is a large range of values in which we can detect the perturbations.
Okay. Any other question? What does change mean in network? One of the other questions. What does change means in network?
Well, that's a very good question, and actually here we see that I was just putting that under the rug. In fact, depending on the distances you use, you will detect different types of changes. For instance, in the original paper by Masuda and Holm, if you look at basically the same data, they obtained that the lunch of the second day is similar to the lunch of the first day, while we obtain that they are different. And that's because we're measuring different things. In their case, they use a spectral distance, which does not look at the fine grain detail, but rather at the kind of main properties of the network. While here we look at the similarity of the neighborhoods of each individual. So those can change, but the network be similar in terms of spectrum of eigenvalues. So change itself is not well defined, but here we have social change, and that's what we can detect.
Okay. So we have two more questions. One is, have you looked at stability of temporal cores communities under various choices of alpha? And the second one, could this method be used somehow to consider the temporal network data as a continuous time dynamics?
So no for the first part, because we haven't had time to look at a bunch of data sets and temporal networks with kind of tunable community structures or these kind of things. And in the second case, yes, that's basically the idea, similarly to this paper, in which basically we want now at any time we want to have a picture of the social system, which is informed by everything that has occurred until now, without the big aggregation that blurs out all the dynamics.
Okay, and last very short question, how is it possible to segment network into time windows, for example, for tracking community evolution?
So that is arbitrary. That's the point of you take all the events that occur during a certain time window, and this time window is arbitrary. So you don't really have any a priori information on how to tune this, and that is really the idea that are behind papers like the one of Naoki and Peter, is really you have a first tau, which is kind of arbitrary, but then using this hierarchical clustering method, you find states that can last much longer and have lengths that are not known a priori.
Okay, thank you so much.
I will stop
Thank
the
you for
sharing.
talk.
Thank you.
Thank you. And the second speaker is Bartłomiej Nowak. Hi.
Wait, hello, do you hear me?
Yes, yes, we can hear you.
Thank you, great. Give me a sec. I need to share the screen with you. Okay, do you see the presentation, guys?
Yes, we see the presentation.
Great. To start it here. Nice. So I will start, I think. Okay, so my name is Bartłomiej Nowak, and first of all, I want to say thank you to the organizing committee for giving me this great opportunity to sit in front of you and give this talk to you. And I want to share with you my work within the symmetrical threshold model with independence and our search for the social hysteresis. And the first thing first, we need to ask two questions. First one, why threshold models? And I think each of you here in this place can think about the real life situations in which we need to have some majority to perform with some decisions like voting or choosing food with your friends for today's evening or something like that. And the second question is, why do we care about the hysteresis? Why we want to search this hysteresis with by some models? And the hysteresis, in a sense, is the dependency between the initial state and the final outcome of the system. And this is not only the fancy buzzword written in the papers, but this is a real case observed in some in some research, like in these examples for the animal species, when we can look for the some initial state based on the temperature or the predatory risk level, it can dramatically give us the different outcome in a sense of the stationary state of the dynamics on anything else what you can imagine. But also we can track such phenomena in a theoretical way, like physicists. So for example, like in the Q-Voter model, when we want to track how parameters affect the existence of the hysteresis. And researchers prove that the existence of some noise causes the existence of hysteresis. Like the Q-Voter model, when the existence of independence causes the existence of hysteresis if the level of the influence group is an appropriate one. So for example, for the size of the group of influence bigger than 5. Contrary, in the majority vote models, so when the group of influence is not performed by some unanimity, but we need to have some majority in the system. So more than 15% in our neighborhood need to perform some decisions to influence us. And this additional noise in terms of independence and any other noise do not cause the hysteresis at all. And this is because one of the fundamental ingredients next to the topology structure and the high average node degree and as such other stuff is the high level of inertia, which can be caused in this system, for example, by some external parameter theta, and the level of this parameter tells me what is the value of probability of not being influenced. If this probability is high, I start to observe the hysteresis in the system. If this probability is really low, the hysteresis is not appeared. And I want to check if these cases are the case in my version of the symmetrical threshold model, which I will present you in a minute. So I will start from the description of a model. We perform the simple agent-based modeling on a Watts-Strogatz network, which allows us to tune between the random network, the fully random network, the regular one, and we also have the parameter k, which describes the average number of neighbors. And we put on this topology agents in such a way one node is one agent, and the link between the agents describes some kind of interaction. So for example, if two agents are connected with the link, they know each other, so they can interact Okay, agents are binary, so simply positive attitudes are mapped to the value 1, negative attitudes are mapped to the value -1, and this gives us the simple case that we have yes no value, and we can track everything by calculating simply the average opinion, so namely concentration, which is the fraction of positive agents in my system. Agents can be affected by two forces: conformity, so mechanism which encourage my agents to act in the same way as the neighborhood, and the independence, in which I do not care about the neighborhood at all. My simulation takes the Monte Carlo steps, in each Monte Carlo steps I perform n, so the size of the system elementary updates, and in each elementary update I randomly pick an agent. This agent can have one of two possible values, 1 or -1, and he can act in two different ways: conformity one and independent one, with some probability p. So with probability p, he behaves like the independent one, and with probability 1 minus p, he will be the conformist in this step. In the conformity case, this agent looks on his neighborhood and check what kind of distribution of opinions in there. And for example, if the portion of green agents is bigger than some given threshold R, for example, this R can be 0.6, this agent chosen at the beginning will change his opinion to the value 1. Of course, if he has this value at the beginning, he will not change his value. He will stay with this value 1. In the opposite case, so for example, when the majority of the opinions in the system will be red one, bigger than the threshold, he will change his value to -1. In the independence case, he flipped the coin and changed the value 1 or -1, so he chose one of the options. So this is quite simple case. And we want to perform the Monte Carlo simulations and check how the stationary solutions will change due to some parameters of the model. And also we can track everything by some analytical calculation, by pair approximation approach. And in this approach, we produce two true equations. First one will describe the dynamics for the concentration of my opinions. The second one will describe the dynamics for the active links, so links which connects agents with different opinions. And we can clearly see that this equation shows the dependency on the network structure as well as the average number of neighbors. And in upcoming pictures, upcoming slides, I will present the solutions of this equation by some lines, and the stability will be described by the dashed line and solid lines, respectively. And outcome of the Monte Carlo simulations will be presented in points. So first of all, we observed a very good agreement between my simulations from the agent-based model and the outcome from the theoretical reasoning, so the pair approximation approach. And what is important here, we can back to the majority case. So we can pick the threshold equal to 0.5. So we are in the majority case, and here we do not observe any discontinuous phase transition, any hysteresis at all. But when we start increasing this threshold, our hysteresis start to appear, and also the dependency on the topology appears here, which was observed in the dynamics described by the equations. Namely, the size of the hysteresis increases with the average value of the degree of the node. So this is quite important, that we can improve the simple majority case to some supermajority by state the value of the threshold, and this leads us to improving the model by including this level of inertia, let's say. Why? Because one of the fundamental ingredients of the discontinuous phase transition within these models are the high value of the neighborhood. So I need to have a big neighborhood. But also this large threshold, these two values connected with each other give me the situation in which I very hard to collect sufficient majority, some group of agents with the same opinion to affect my other agents. So the probability of not being influenced by my neighborhood is really high. Also, when we look how the size of the hysteresis behaves in terms of parameters, we'll observe some maximum, we'll observe some optimal value between these two values, 0.6 and 0.8, which one may consider in some research, social research, or maybe maybe observed in TV in some commercials, that this value might be optimal in a sense that for this threshold values, the range, let's say the space in which we can perform some moves to influence our agents, our neighbors, our friends, is the wider. And more or less going to the conclusion, in binary type of models, we can observe the hysteresis, so the dependency between the initial condition and the final state, if the level of inertia appeared in the system on an appropriate level. So we can do it by putting some external parameters. So for example, like in majority vote model, we can put theta and increase this theta and check how it affects my model, and it can produce the social hysteresis here. Also, we can produce a supermajority like we did in our model, but you can imagine many ways to make hard to collect the group of influence and affect your agents, which should produce some kind of phenomena in your systems. So basically, we see that the value of the threshold matters. So simple majority might not be sufficient. The average number of neighbors is also quite crucial, because for the low numbers of for the small groups, maybe important the unanimity, not the supermajority. But for some bigger groups, the supermajority may play the crucial role. And also we can observe that hysteresis, so that's dependency between the initial condition and final outcome, can obtain some optimal values, can perform some maximus. And this is pretty much all what I want to share with you today. Everything, if you have some questions, you're welcome. But you can also read everything in this paper, which was produced in May in this year. And this is everything from me. Thank you very much.
Thank you. Okay. Now the question comes. What do you mean by hysteresis? One of the questions.
What I mean by hysteresis. Okay. Maybe I will show this on this picture. So when I perform the simulation, I start from some initial condition. So for example, at the beginning, I start with the concentration of positive agents equal to 0.52. Okay, so I'm more or less bigger than this dashed line here. Okay, and my system converge to one of these values here because they are my stationary states. And what I mean by hysteresis, this hysteresis is appeared like here. I have this this coexistence region. What I mean here, that from one initial condition, namely, for example, initial condition in which each agent in the system has the same opinion, so the concentration is equal to 1, I will lie here, like these points. But for other initial condition, namely 0.5, I will finish in the stationary states like this. So I have different outcome based on the initial condition. So this is the hysteresis, this region here, okay? I hope this is quite clear because I'm pretty messy here.
And could you show the paper again?
Paper again, yeah, sure. I can also put a link in the chat if you want.
Yeah,
I hope it will be helpful.
Are there any quick questions? I think it's okay. Okay. Okay, thank you.
Thank you.
And Neil Maclaren. Hi.
Hello.
Hello.
I'm going to share a video in just a second. I have a recorded presentation. I just want to thank you, the monitor, and thank everyone for being here, as well as the conference organizers. So just let me share my screen. Let's see here. Do that.
Hello everyone, my name is Neil Maclaren. Thank you all for being here today. I will be in the chat window, so please feel free to ask questions or make comments at any time. I want to thank my co-authors who are listed there. Without them, this research simply would not be possible. So I'd like to talk about sociometric structure today, so the patterns of interactions within a group. And specifically, I want to look at leaders, and I'd like to make a network model of that group that we're looking at that will tell me who the leader is, and I'd like it to be based on behavior, specifically conversational interruptions. So I will talk about why that's important, how we make these networks, and some results. So first of all, I can be pretty confident that a work group will have a leader. So somebody in that group will receive relatively more esteem and will have more influence on others in the group. There could be more than one, but there will be one. The problem is, as a researcher, how do I identify that individual in a principled way? So there's a couple different ways that we might do this. One is we might ask the other members of the group who the leader is. They're the experts, after all. The problem with asking them, though, is that we could get bias, and we don't really know what bias we're getting or what direction it's influencing the results. It could be non-random and unknown, so that potentially poses a problem for us. Another thing we could do is we could ask an organization who the team leader is, or we could assign them ourselves. And that could definitely provide us some information, but unfortunately, probably the biggest problem with that is that it may not actually match who the de facto leader is, who actually has the most influence on the group. And the last thing that we could do is we could take a measurement. We could say, how much time did everybody speak for? Because participation quantity is known to be associated with attributions, and it's also associated with some pretty relevant behaviors, such as information sharing. Speaking time, however, does not give us a dyadic relationship. So in a small group, a lot of times group members speak to the whole group. It would be difficult for us to unambiguously say that one person was speaking to one other person. And so it would be difficult to reflect theory of sociometric structure, which is essentially dyadic. And we would like to use a network to represent that dyadic relationship at the group level. The problem is, given what I've talked about, what should we use as the edges? It's not necessarily obvious. We need something that we can uniformly define across all of the interactions and all of the group members, and we might like to not deal with some of the problems that we've just discussed. And I think the answer has to do with sociometric status. So that's the difference in the relative esteem that different individuals have in the group. And status is something that we as humans spend a lot of time on. We care about it, we perceive it, we attribute it to others, we perceive it in ourselves. It's pretty important to us. And also, fortunately, it has been assessed as a behavior, so as a nonverbal behavior. So a nonverbal behavior is a potentially communicative, potentially not, but it's a thing that someone does that's not specifically the words involved in communication. It's not an antecedent, like a role assignment would be, and it's not an outcome, the way that co-participant attributions might be. So we can look at the performance behaviors, and here specifically we're concerned with speaking data because it can be defined across a wide range of contexts, and speaking is very important in small groups, particularly work groups. So that, what you're looking at there is diarized speaking data. It's data for whom we know who spoke when. And we can turn that data into what I'm going to call an interruption network. So let's talk through that now. So we have, in the schematic, we have 3 participants, A, B, and C. They speak in the gray boxes. They're not speaking otherwise. That is an interruption. So here, B started speaking while A was speaking and continued after A stopped. And the direction of the edge in the interruption network is going to go from A to B, and that's because A is deferring to B in some way. We don't really know why. It may not be possible to know why, and there could be a lot of reasons, but we do know that for whatever reason, A sort of made way for B. There is another interruption, but this is not an interruption because A kept speaking. And this is not necessarily an unsuccessful interruption. It could be qualitatively different, so we're not going to consider it here. So this is the interruption network that we would build from this schematic interaction. And you can see the edges are going from C to A to B, and so we can use PageRank centrality to capture this idea in a larger network. And we'll use PageRank because it can account for the presence of isolated nodes, which you'll see. A word about the data. The data is publicly available now. It's hosted by the Open Repository at Binghamton University, and it's associated with a paper that we had published earlier in the year, so that you can download this data yourself. So the data consists of 33 groups of student participants. They ranged in size from 4 to 10. And they're all trying to solve some sort of a problem, and we just videotape them doing this problem together. There's one participant who's assigned to work a computer, but other than that, I'm sorry, they're randomly assigned to work a computer, but other than that, we let them do whatever they're going to do to solve the problem. We do take participant attributions immediately after the interaction period. We take these votes. And then I should say that the data is diarized by hand using video annotation software. So this is what we get from this method. This is an interruption network. The triangles are males, the circles are females. The thickness of the edge is proportionate to the number of times there's an interruption that went in that direction, and the color is proportional to page rank, blue being low page rank, and yellow being the highest. So here is a vote network. This is for the same group. These are the votes between individuals with a source and a target. Okay, so interruptions empirically are correlated with speaking time. And so to assess whether or not we're actually getting unique information from the interruptions, we took a null to be that an interruption is just a random occurrence based on two group members speaking somewhat closely together in time. And the way we addressed this was with a simulation. So we said, okay, so let's increase the probability of randomly reversing an edge so that instead of I pointing to J, J points to I. And we'll ask how that changes which node is chosen as the maximum page rank centrality node. And this is that data. And we can see that at the sample level, increasing the probability of reversing an edge does reduce the match between the simulated and the empirical leaders. And so we do find that there is some unique information that's encoded in these interruption networks. So not only can we unambiguously associate A with B, we can say that the direction of that association matters as well. And I should say that these are small networks with lots of isolated nodes, so there are plenty of complete networks that resist this particular simulation. So another thing that we can do is that we can keep the node activity the same, the degree histogram the same, but randomize the targets of all the edges. So this is done in motif analysis, looking at the mesoscale structures in the networks. And in the interruption networks, we find that the line motif here appears more often than we would expect by chance. And in fact, it's the only motif that does. So other motifs that you might expect, such as the transitive triad here, are not found more likely than you might expect. And the cyclic triad here also not found more likely than one might expect. So with that information at hand, we turned to some exponential random graph models to give us a better idea of what was going on with the gender of the nodes. So here what we're doing is we're controlling for density and we're controlling for mutuality between the nodes, and we're asking, is gender associated with an increase in the number of in edges in the two different networks? I'm sorry, the two different ways of representing the group, the vote networks on top and the interruption networks on the bottom. And we can see that in the vote networks, it does make a difference. So males receive more edges than females, but males and female participants and female participants didn't differ in their out edges and the votes that they cast. In the interruption networks, however, we don't see that difference. And so what we're looking at here is a situation in which male and female participants are behaving similarly, but being rated differently. And here's just an anecdotal way to visualize that. Looking at the same networks that we've been looking at before, we can focus on participants 4 and 5, and we can see that in the vote network, page rank is higher for the male, participant 4, but it's the same in the interruption network. So what I conclude from this, specifically with respect to bias, is that the interruption networks seem to be suggesting that male and female participants are acting in a leadership manner equivalently. There doesn't seem to be a gender difference in the influence that they have over each other, but there is a difference in the ratings, suggesting bias in the ratings. More generally, we've taken our theory of sociometric structure, we've implemented it in a network model that makes sense. We've assessed behaviors of participants directly as we can, and we've made the model from that. It's unobtrusive data collection, so we can let the participants keep doing what they're doing without stopping them to ask questions in order to do this this assessment procedure. So for future directions, we're working on improving diarization techniques from an algorithmic perspective, as well as improving our data collection so that we can get better data for human coders. We're also looking at ways that we can use multiple networks of different kinds of behaviors to get a more complete picture of what's going on in the group. And we're looking eventually at building better leader assessment and selection protocols, as well as leader training, improving leader training for the organizational incumbents. I want to acknowledge support from the U.S. Army Research Institute, as well as our home universities of Binghamton University and the University of Oklahoma, as well as thanks to the participants who made this research possible. And thank you. I will be again in the chat window if you have any questions or comments, and my email, GitHub, and data download link are there. Thank you.
Thank you. Are there any questions? Oh, there's one. I really liked your methodological approach, but I'm a bit confused. You assume interruption is an indicator of status, and then show it doesn't quite match the socially perceived status. Isn't it a correct interpretation rather than labeling the socially perceived status as biased? From Taha, yes, sir.
So I think the question is the interruption the correct representation, or is the vote the correct representation? And I think what we're able to show is that they're certainly different. But if the interpretation of the interruption as the person who was interrupted had to actually stop talking in order for the other person to keep talking, in order for that to be counted as an interruption, that's a certain amount of behavioral deference. And so what I think the data shows is that that behavioral deference is not associated with gender in a meaningful way, whereas the votes are. So males are receiving more votes, even though their interruption behavior or deference behavior, depending on which way you want to look at it, isn't actually different from the female group members. So in terms of is one correct or the other, obviously votes, are consequential. That's an important characteristic. But what we're able to show, I think, is that the behavior is not differing between male and female group members.
Okay. Would it make sense to analyze data sets where we know the ground truth, e.g. military?
Absolutely, and I would definitely want to do that in the future. I would consider this a lab methods building phase. We want to make sure that it works generally, and that's actually one of the things I'm specifically interested in. Is can we look at a group where we know the assigned leader, and can we assess whether or not the behaviors match or don't match the assigned hierarchy. So it's possible, for example, that we could have an assigned leader that's simply not controlling the conversation or is not influencing the conversation. I'd like to be able to detect that. And so that is absolutely where I think we should be going with this kind of research.
Okay. Are there any short question, quick question? Okay, I think it's on time. Otherwise we run out of time. Thank you so much.
Thank you.
Thank you to all speakers and attendants, and stay happy. Okay.